I want to have one of put Sarah back as number one.
There we go.
I want to go back.
All right. I will begin with a word of prayer. There we go. Dear Heavenly Father, we thank you for this day. I thank you again for these students. Just ask you to bless our work today. Help us to glorify you in what we do. And we just thank you again, Lord, for your many blessings. In your name I pray, Lord Jesus. Amen. All right, so let me get you guys started on a problem. So I'll write it over here. F of x equals 2 plus e to the x minus 3. So part A is f 1 to 1. B, if possible, find formula for y equals f inverse of x. And then C, graph y equals f of x and y equals f inverse of x. So I guess I'm kind of giving it away. Apparently it is possible to find the inverse. But anyway, there's what I want you guys to chew on while I am cleaning the boards and top hatting for the next 3 minutes. Come on. All right. So there we go. Top hat's over there. So do what you will with it. So what do you guys think? Is this function, so example 1, we have f of x equal 2 plus e to the x minus 3. Is this function 1 to 1? What do you guys think? And how did you prove this? Because I did not say that.
You said you basically gave it away.
I said that it's invertible, so if you already knew that invertible functions are 1 to 1, then you know it, I guess. But did I ever say that? I mean, I might have. It's true. It is true, of course, that invertible functions are 1 to 1. That is true. So one way we could do part A would be like algebraic. So if we suppose f of A is equal to f of B, that would tell me that 2 plus e to the a minus 3 equals 2 plus e to the b minus 3, right? subtracting 2 from both sides would give me e to the a minus 3 equals e to the b minus 3, right? And then by the one-to-one property of the exponential, that tells me that a minus 3 is equal to b minus 3. And then add 3 to both sides, lo and behold, a equals to b. So this would algebraically show that the function was one-to-one. If you have equal outputs, you've got the same input, right? Of course, you could also graph the function, right? And if you were to graph it, what would the graph look like? Basically, you're taking the exponential function, you're moving it up 2 and over 3, right? So essentially the graph, it has a horizontal asymptote of 2, right? And if you look at what you know, if I plug in 3, when I plug in 3, I get what? I get 2 plus e to the 0, which is 3. So I think I get, is that right? Three? Is f of 3 equal to 3? I don't know why. For some reason that's bothering me. 2 plus e to the 3 minus 3 is 2 plus e to the 0, which is 2 plus 1, which is, yeah, it's 3. So 3 is a point on this graph. So 3 is like here, right? And so the graph, and what's f of 0? 2 plus e to the minus 3. So 2 plus e to the minus 3 is just a little bit bigger. It's like 2 plus 1/27th, roughly speaking. I mean, it's really, really close to 2. So it's something like that. So you got this point, you got that point, and so like what's going on here is something like this, all right? So there you go. There's a graph of y equals 2 plus e to the x minus 3. So this point here was 3, apparently. And let's see, let me go 1 point over. So at 4, where are we at? At 4 what? F of 4 is what? 2 plus e to the 4 minus 3, which is e to the 1, right? So e to the 1 is about 2.7, so we're about like 4.7-ish. So it's, so my picture's probably a little bit off. It's,
E always be the same.
e is a fixed number, so yeah.
I was going to ask that. E is that special E that you said?
Yeah, e is like pi. It's a fixed number. Okay, so anyway, here's an attempt at the graph. All right. Anyway, so my point to you is we could also see that the function's one-to-one because it is an exponential. It passes the what? The horizontal line test, right? So it's one-to-one. And in some sense, that would just be forward-looking because you notice in part C, you're going to have to graph f in the inverse anyway, so you might as well graph it. We can add to this graph for part C, right? So for part B, we're supposed to do what? Find the formula. So that's that 4-step process, remember? Step number 1, we write what? Y equals to the formula. So the formula here, 2 plus e to the x minus 3, right? That's our starting point. Step number 2, solve for x. How are you going to solve for x? I mean, as a general point of order, when you want to solve for some variable, you try to isolate it, right? So we can move the 2 to the other side for sure. We get y minus 2 equals e to the x minus 3, right? Well, that x is still stuck up there in the argument of the exponential. So how can we How can we set it loose? What can we do here?
Take the natural log.
Take the natural log of both sides? I like that. So if we take the natural log of both sides, that will make the exponential go away. Right? See, so natural log and exponential inverse functions, which just leaves us with x minus 3 here. And I think now we can solve for x, right? X equals to 3 plus the natural log of y minus 2. So at this point, we've reached the end of step 2 in the algorithm for finding the formula. So I referred to this originally as like stuff in y, right? It's our formula for the inverse function. So we identify that, oh, well, this is really f inverse of y, right? That was my step 3 in that algorithm. And then the step 4, if we need it, is to change y to x, right? So step 4, and I did ask us to find the formula y equals f inverse of x, right? So f inverse of x here is 3 plus the natural log of x minus 2. And there you go, that's the formula right there. Which is kind of neat, right? Because it involves, it's really so much just like the original formula, right? But with the 2 and the 3 kind of flipped over in their roles, and instead of exponential, you got log. It doesn't always work out like this in terms of like the pattern, but the pattern here is particularly nice for the formula. Now can you graph that? So there's various ways of graphing it. But one way we could graph it is to notice that what was before a horizontal asymptote now becomes a vertical asymptote, right? So like we had a horizontal asymptote of 2. Now we're going to have a vertical asymptote, x equals to 2. Vertical asymptote for the inverse function, right? And the points on the graph, they get flipped, yeah? So this 3 point's kind of funny because that means that one's on both, isn't it? So that point stays put. How about the other one? This becomes 2 plus e comma 4 on the other graph. So that we trade for about a 6.7. So it's kind of like down here somewhere. So that's approximately 6.7 comma 4-ish. And this is another point on the graph. I think I'm not doing it quite right. It's kind of up here. Anyway, so it looks something like this. I'm not sure exactly what happens here. I think probably there's a crossover there. I'm not sure without doing more work on this one. I suspect it looks more like, I suspect that there's like 2 points of intersection. There's 1 point here and 1 point here, something like that. I don't know for sure what that looks like without getting, I'd have to get Desmos out to do better. If you'll let me misbehave for a moment here. What? Oh, interesting. That's funny. It actually is just the point of intersection of these two. That's weird. I'll show you. So like the red graph is the function and the blue graph is the inverse function. It really is just that 1 point where they touch. Just to give you a sense of how weird this is to me, in the earlier sections, guys, I worked out this one. And I didn't realize I was changing it so much, but I think if I do like 4 plus e to the x minus 3, it works out different. So if that's the function, then the inverse function, I can get right quick. So in contrast here, if I do oh, weird. Yeah, now they don't touch at all. I'm thinking maybe I had them flip. Maybe I had like a 3 here and a 4 up there. Well, now we're back where I started again. What happens if I put a 2 there and a... Oh, there we go. So that was what happened in my earlier class. I had picked numbers like more like that. And what's interesting here is with this one, if you try to find these points of intersection, like algebraically, I don't think you can do it. Like not with algebra anyway. Look, what would the points of intersection here look like? You'd have to solve 2 plus e to the x minus 4, right? Equals to 4 plus the natural log of x minus 2. Can you solve that? I mean, try. What would happen if you tried to solve this? I would get e to the x minus 4 is equal to 2 plus log of x minus 2, right? And then I take the natural log of both sides, and I get x minus 4 equals to the natural log of 2 plus the natural log of x minus 2. And so no good comes of methods that you try to solve this with, right? And yet, the problem I stated today had a nice solution that we found by accident. Like the graph of the function and its inverse intersect at 3. I was just weirded out by this because like I looked at this problem earlier today and I realized I couldn't find the points of intersection without solving an equation like this, which is actually something we can't do.
Is it mathematically impossible?
I mean, there's the approximate solution right there. Desmos found it for you. See? 2.159. You know? Yep. Oh, the wire came out. Oh, thank you. We can't have that. It's okay. It's okay. It's just that this wire's gotten all too tangled. I took my daughter to see Tangled in the movie theater once upon a time when she was like 3. It was fun. Do you guys remember Tangled in the do you remember the scene in Tangled where they kidnap? Oh, I'm sorry, spoiler alert. They like kidnap the main character.
Yes.
Remember that? So when that happens, like there are probably like 20 people in the theater, right? Because I'm sure we were going to the Dollar Theater. You guys realize that jump park over there, that worthless jump park, used to be a Dollar Theater, right? It's true. Once upon a time. But when they kidnapped the main character, my daughter screamed in the theater, "No!" It was awesome. Everyone's like, "What?" It's like she was so into that movie. It was great. It's great. But anyway, I digress. Okay, let me put this away. You guys got questions about homework? So I just wanted to start us with an example that has, I don't know if there's an example quite like this in your homework, but this is what we should be understanding because we've already talked about inverse functions, about one-to-one functions. We now know algebra, where we can solve equations involving natural logs and exponentials, right? So we can put those two ideas together and do this example is my point, right? This may not literally be a problem in your homework, but it is a problem which is important to me. I could put it on the test, sure. Let's see here. So example, I will call it, let's see here, example, where we are. That was example 1, wasn't it? So example 2 then. Do you guys got questions? If not, I will forge ahead here with homework problems. Go for it. You've got e to the 11x minus 4 equals to what?
Minus 1.
Oh, minus 1.
No, like 11x minus 1. Not instead of 4, it's a 1.
Oh, okay. And then what?
It's e to the 9 in parentheses and then to the x.
Sure, we can do that one. So here we need to use the, oh, this reminds me, I still owe you guys a proof of the laws of logarithms, so we'll get back to that. But okay, so here we have e to the 11x minus 1 equals e to the 9x, right? And then we can either use the one-to-one property for the exponential, right? Or if you like, we could take the natural log of both sides, right? So if we take the natural log of both sides, what do we get? Mm-hmm. You say 11x minus 1 equals to 9x, right? Which then gives me 2x equals to 1, which gives me x equals to 1/2. There you go. Other questions? Let's see here if I can work another one here.
Could you do the one with decimals?
Do the what?
Do one with decimals?
One with decimals?
Yeah.
Well, I suppose. Example 3, we could have something like 2 to the x equals to 5. Solve this, right? So this is essentially number 10. So I made number 10 from week 12 homework, okay? So number 10 from week 12.
Wait, this is week 12.
This is week 12. There's really not much difference between the week 11 and week 12 homework. There are some sort of mid-level bosses towards the end of week 12 homework, whereas you pretty much only have like level 1 enemies in week 11. I will show you how to kill some of the bosses here in a minute. But this is still level 1, right? Because here, again, the answer is just, you just natural log the thing, right? We take the natural log of both sides, we get what? So this gives us x log 2 equals log 5, which gives us x is equal to the natural log of 5 over the natural log of 2. Now, how else can you express that as a log base 2? By the change of base formula, this is also equal to log base 2 of 5, all right? And then, if you want, per Francisco's demand request, we can find a decimal answer here, right? So either you got a calculator which will do log base 2 of 5, right? Like mine will. Or you could just do natural log of 5 divided by natural log of 2. And I'll give you the first, like, a few digits in here. This is 2.5 32193. Something like that.
Yeah, that's not what I meant exactly. I meant a decimal raised to a power.
A decimal raised to a power.
Mm-hmm.
So you mean something like 0.567 raised to the 3t minus 1 equals to 2?
Yeah.
So yeah, we solve those problems the same way. So you just hit both sides with natural log. We use the property of the natural log that the power pulls out. And then, let's see here. So that's going to give me 3t natural log of 0.567 equals natural log of 2 plus natural log of 0.567. Then I can solve for t. Like that. And then, of course, if you want, you can find the decimal answer, right? Get out your handy dandy calculator, plug it in there, and see what you get. If I do that, I get, yowzers, approximately minus 0.07388-ish. So that's what you're looking for, something like that? Yes, no, maybe so? Okay. So this is an uglified version of like number 12 in homework 12. Yeah.
Can you do 64 to the 5x?
Let me just copy it down. 64 to the what?
5x,
64 to the 5x power equal to what?
16x plus 1.
X plus 1. So this would be my example 5, I guess. All right, we'll try this one. So do you guys have any ideas? I mean, the lazy way to do any of these problems is just to take the natural log of both sides. If we want to think more, we could go, well, these are both powers of 4, right?
They are.
I mean, this is 4 cubed to the 5x. This is 4 squared to the x plus 1, which gives us 4 to the 15x equals 4 to the 2x plus 2. Then by the one-to-one property of the exponential function base 4, we just get 15x equals 2x plus 2, which gives us 13x equals to 2, which gives us x is 2 over 13. Yup. So those ones aren't, I mean, these are kind of all the same problem. In a sense. I mean, you can just take the natural log of both sides and then deal with logs of 64 and 16, and you'd still get that same answer. If you weren't trying to be clever about it, you know. That same problem here I could solve without this step, you know. I just take natural log of 64 to the 5x equals natural log of 16 to the x plus 1. That gives me 5x log of 64 equals x plus 1 times log of 16, which gives me 5x, which gives me x times 5 log 64 minus log 16 equals to log 16, which then gives me x is equal to log 16 over, 5 log 64 minus log 16. Which might not look like the same answer right off first glance, right? But what that is the natural log of 16 divided by the natural log of 64 to the 5th power divided by 16. Yeah. Now I'm going to have to think. Well, anyway, that is the same number, but it's not at all obvious that it is the same number. You can try it out and see what happens when you plug it in your calculator, see if you don't get the same thing.
So if we get a question on the test like that, just use the first one, right?
Well, I think the first approach is always the best approach here, right? But if for some reason you lack insight, you can take the natural log of both sides, but then you've got some calculator work to do at the end, right? So, you know, natural log of 16 divided by natural log of 64 to the 5th power divided by 16. And of course, you could have just punched it in like this, right? You didn't have to simplify using powers of log properties if you wanted to. And my calculator gives me back 2/13 from this. See? Right? I'm not making it up. Yeah? Okay. Mean girl verified, yes?
Yeah.
Okay, okay. It's good. See? So yeah. Yeah. But anyway, is that the right? I think that the second way I did it is absolutely, it's the wrong way to do it, right?
It's the harder way.
It's brute force is what, this is brute force, all right? It's not clever, it's just, you know natural log is going to get rid of exponentials. Okay, let's go on. We'll try another one here. How about, I mean, there are problems which demand the natural log to be used. And so, like, this one is such a one. What example am I on? I lost track. 6, thank you. So this one is number 13. So here you've got 2 to the x minus 1 equals 3 to the 2x. See, when you've got two different bases involved, and they're not like related to each other by power, like the 16 and 64, those say, hey, we're really just powers of 2 or 4 or something, right? Fine, we can make those look alike. 2 and 3, oil and water, right? These are apples and oranges. They're not related. So pretty much natural log's your best bet. So we do natural log of 2 to the x minus 1 equals natural log of 3 to the 2x. Pull down my x minus 1, parentheses, log 2, 2x log 3. And now I put all my x's on one side. So I get, x log 2 minus x times 2 log 3 equals to log 2. So I put everything with x on one side. And so what I really have here is x times the natural log of 2 minus, and hey, we could rewrite that. What's 2 natural log of 3? What is 2 natural log of 3? Do you guys know this? Yeah, it's natural log of 3 squared, right? Also known as 9, right? So we've got, this is really just minus x natural log of 9 equals natural log of 2. So what we got then is x is equal to natural log of 2 divided by natural log of, well, 2/9. Which of course we could also write as natural log of 2 divided by, natural log of 2 minus 3 natural log of 3. Excuse me, 2 natural log of 3. If we hadn't simplified. But anyway, however you write the answer exactly, we can all agree on the decimal form to the first 4 digits is what? get our calculator, calculate it, right? We've got natural log of 2. You gotta get out your slide rule. No, we don't do that, right?
So on the test, can we just leave it as what you have above?
Depends on the instructions. Minus 0.4608. I probably, if I was smart, would say something like, please leave your answer both as an exact expression, this would be exact expression, and a decimal approximation to the first 4 digits. That would be smart on my part, is to ask for both. I should probably do that. But as you can see, even for relatively simple problems like this, you can get really different looking exact answers, right? So like the ways logs combine, it's subtle.
Is there no other way to do it?
Is there no, I mean, there's always another way to do it, you know?
Without brute force?
Like if I had like better balance, I could like do it while standing on 1 foot, for example, you know?
Another method.
But I don't feel like that's going to go well.
So are we able to leave the answer as any one of those? Like the decimal or the,
Again, it depends on the instructions.
but if there are no instructions on like,
Well, there are always instructions.
but I'm just saying if there's not.
Like in your homework, it says like the solution set is blah. Do not round until the final answer. Then round to the nearest thousandth as needed. Use a comma to separate answers as needed. I mean, there's always instructions.
But if there wasn't,
If I ask for an exact answer, then I would want this. But is this the right answer versus that the right answer? Really, unless I finesse my instructions more, it would be hard for me to say one of those is the answer and one is not. Certainly, even if I did have a more finessed set of instructions, it would still be the case that either one of these or the other one of them with like 95% credit versus 100% credit, you know? Because if you've gotten this far, you really understand how to solve this equation, right? So either way, I'm happy the student has got that far. Now, if all the student gives me is no work and this number, I don't really want to give you a lot of credit for that, right? Because I do need to see steps. Like just this number and no work equals not that much credit, all right? I need to see steps in this mathematics. So example 7. Let's work one. So let's look at a mid-level boss here. E to the x squared equals to 148. How are you going to do that one?
Could you log it twice?
Well, I mean, how about, yeah, take the natural log of both sides. That sounds like a good idea. Let's hold off on the second natural log. Let's see if we need it or not. So this gives me x squared, natural log of e, equals to natural log of 148, right? Of course, the natural log of e is what? Is 1. And so if you understand what's going on here, you really could have gone straight to what I'm just writing right now, right? We can go straight from here to here. Why? Because the natural log and the exponential are inverse functions, right? So when I take natural log of e to the x squared, I just get back x squared, right? Anyway, so there we are. Then what do? This means x is what? Plus or minus the square root of the natural log of 148. And there you go. Two solutions. They're your solutions right there. This was problem 14, and they want, I think they want decimal approximations for those. Yeah? So you can punch it in the calculator and find the decimal approximations for that, yeah? All right, so fine. So far, not too bad. I would say this is a mid-level boss. Let's look at another mid-level boss. Example 8. Suppose you're trying to solve 3 to the x plus 2 equals, 2 to the minus x. Oh, that's not it. 2 to the x plus equals 10. There's some problems like this, and I don't think that this should make anybody get stuck, but the fact of the matter is that this will stop some of you in your tracks. You don't know how do you do this? How do you deal with such a problem? What do you do?
Do you subtract 2?
We just subtract 2 from both sides.
And then it's 2 to the power of 10.
Yeah, we have 3 to the x equals to 10, 8, right?
And then 2 to the third power.
Well, okay, yeah, that's 2 to the third power, but does that help you? I mean, I don't know if, I'm not sure that really helps, but because we've got a 3 to the base and base 3, base 2, right? They're not.
So then you have to do that.
Yeah, I think at this point I would just take either log base 3 of both sides if you like. I haven't done enough log base 3. So here, log base 3 of x, 3 to the x equals log base 3 of 8. So we get x equals to log base 3 of 8. There you go. That's the answer. Can you write that answer in terms of natural logs? How would we express it in terms of natural log? We use the change of base formula, right? Change of base formula here would say that this is equal to natural log of 8 over natural log of 3. Which incidentally is exactly what I've gotten if I had taken this, right? See, I would have gotten that same formula if instead of taking log base 3 of the equation, I'd taken natural log of the equation. That would have also gotten me to that same answer, right? So what's the right way to do it? Is it to take log base 3 of both sides, or is it to take the natural log of both sides? Either is fine, really. The question is you do have to pay attention, right? If the book asks you to write your answer in terms of natural logs, then you need to do that, but okay, so finally, let us face a legitimate monster. E to the 2x minus 14 e to the x plus 45 equals to 0. Then example 10, let's say 4 to the x plus 3 times 2 to the x minus 4 equal to 0. So I would say that these problems are the next level up. All right, these are level 2 or level 3 bosses in my view. And so the way to solve these, we have to combine what we're learning with something we know from before. All right, so like this is e to the x squared minus 14 times e to the x plus 45, right? This one we can write as 2 to the x squared plus 3 times 2 to the x minus 4. So example 9, I can make a y equals e to the x substitution. And this gives me what? Y squared minus 14y plus 45 equal to 0. Right? And down here, if I make a y equals 2 to the x substitution for this one, that gives me y squared plus 3y minus 4 equal to 0. Now, both of those quadratics we can factor, right? So these aren't the worst. You could end up with a quadratic where you had to complete the square here. That would be tough. That would be more troublesome, right? That didn't happen to us though. This is what? Y minus what? Y minus what? And down here, can you factor it for me?
Minus what plus 1?
Minus what? Oh, down here? Oh, you're doing this, picking the low-hanging fruit, are we? Okay, so y minus 4 times y plus 1, very good. How about the upper one there, though? How about this? We put a 5 here. Put a 9 over here. Then we've got 45, and we've got 5 plus 9, which is 14. Yeah? Oh, Robert's right. I should put the plus on the 4 and the minus on the other one. Thank you. So what does this mean? This means for example 9, we've got y equals to 5 or y equals to 9, right? Which is to say that e to the x equals to 5 or e to the x is equal to 9, right? We can take the natural log of both of those equations and read off the solution. So that gives me what? The top one, I get x equals to natural log of 5 or x equals to natural log of 9. There you go. Them's your solutions right there. That's number 16 in week 12. Number 16 is like this one, okay? Week 12 homework's like that. Example 10 I just made up. It's worse, even though the factoring's easier. Because what you're looking at here is y equals minus 4, yeah? Or y equals to 1. Minus 4 gives us what? Minus 4 equals 2 to the x, yeah? Sorry my y's and my 4's look so much alike. That's an unfortunate coincidence here. So minus 4 equals 2 to the x, or 1 equals 2 to the x, you know? What is one of the principal properties of the exponential is this. This is like mission critical. Exponentials are positive, right? So that means this y equals minus 4 is an extraneous solution. It is a solution to the quadratic, but its solution is useless because this has no solution, right? No solution. You can't have minus 4 equal 2 to the x. That is not achievable with real variables. And so on the other hand, the second one gives me x equal to what? You shouldn't even need a calculator for that one. How can we get 2 to the x equal to 1? We must put, yeah, like you said, x equal to 0. So the only solution to example 10 is x equal to 0. And if you start thinking about these quadratic problems, all of the different logical possibilities that you've seen before with quadratics could happen here, right? You could have the quadratic work out to both positive, like example 9. It could be one positive, one negative, like example 10, right? You could have other examples where both of your quadratic solutions were negative, so there'd be no solutions, right? There are other problems where you work out the quadratic and it works out to like a complex solution. Again, there would be no real solutions, right? There's all kinds of like different possibilities that could happen with these kind of problems. But anyway, that's a pretty good stopping point here. Wednesday, we're going to transition to more looking at problems that are like number 17 or number 18 in your homework from week 12, okay? So, and I will circle back and talk about the Richter scale at some point.
I have a question.
Thanks. You got it?